What if the very fabric of reality is not what it seems? What if the rules that govern the universe, rules we've taken for granted for centuries, are just the tip of an unimaginably complex iceberg? Today, we're diving into one of the most mind-bending mysteries of all, quantum gravity. This is the frontier where the infinitely small meets the infinitely large, where the laws of quantum mechanics clash with the cosmic dance of general relativity. And here's the kicker: scientists still don't have all the answers, but what they do have are theories, 30 of them, to be exact, that could reshape everything we know about space, time, and the very nature of existence. In this video, we're going to explore these 30 theories, each one a unique attempt to crack the code of quantum gravity. From the mind-blowing idea that spacetime might be made of tiny loops, to the possibility that our universe is a hologram projected from the edge of reality, these theories aren't just science fiction, they're the cutting edge of human understanding. And trust me, by the end of this journey, you'll see the universe in a whole new light. So, buckle up, because we're about to take a deep dive into the mysteries of quantum gravity, and trust me, it's going to be a wild ride. Let's get started. Now, let's step into the first theory on our journey: loop quantum gravity. This groundbreaking idea takes us to the very heart of spacetime itself, proposing that it isn't smooth and continuous, as Einstein's general relativity suggests, but instead made up of tiny, indivisible loops. Imagine spacetime as a fabric woven from these loops, each one a fundamental building block of reality. This theory, championed by physicists like Carlo Rovelli and Smolin, seeks to bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that have stubbornly refused to play nice with each other. At its core, loop quantum gravity suggests that spacetime is quantized, meaning it comes in discrete, tiny packets rather than being infinitely divisible. This idea flips our understanding of the universe on its head, offering a way to avoid the infinities and paradoxes that arise when trying to combine quantum mechanics with gravity. But what does this mean for the cosmos? Well, for starters, it could revolutionize our understanding of black holes. Instead of a singularity, a point of infinite density at the center of a black hole, loop quantum gravity predicts a quantum bounce, where matter is compressed to a certain point and then rebounds, potentially avoiding the singularity altogether. And then there's the Big Bang. Loop quantum gravity suggests that the universe didn't start from a singularity, but rather emerged from a previous collapsing phase, like a cosmic bounce. This idea not only challenges our traditional view of the Big Bang, but also opens up fascinating possibilities for what might have come before it. So, while loop quantum gravity is still a work in progress, it's already reshaping how we think about the universe's most extreme environments: black holes, the Big Bang, and the very fabric of spacetime itself. And with that, we're just scratching the surface of what this theory has to offer. Next up, we'll explore another mind-bending idea: string theory. Now, let's shift our focus to another fascinating theory that has captivated physicists for decades: string theory. Unlike loop quantum gravity, which reimagines spacetime as a network of loops, string theory takes a completely different approach. It suggests that the fundamental building blocks of the universe aren't point-like particles, as we've traditionally thought, but tiny, one-dimensional strings. These strings vibrate at different frequencies, and it's these vibrations that give rise to the particles we observe, like electrons, quarks, and even the elusive graviton, the hypothetical particle that carries the force of gravity. At its heart, string theory is an attempt to unify all the forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces into a single, elegant framework. This makes it a strong contender for a theory of quantum gravity, as it naturally incorporates gravity into the quantum world. But here's where things get even more intriguing. String theory requires extra dimensions to work. While we're used to thinking of the universe in 3 spatial dimensions plus time, string theory suggests there could be as many as 10 or even 11 dimensions. These extra dimensions are thought to be curled up so tightly that we can't perceive them in our everyday lives, but they play a crucial role in the behavior of strings. However, string theory isn't without its challenges. One of the biggest hurdles is the lack of experimental evidence. Because the strings are so incredibly tiny, far smaller than anything we can currently observe, it's been nearly impossible to test the theory directly. This has led some critics to argue that string theory is more of a mathematical framework than a physical one. Yet, despite these challenges, string theory remains one of the most promising avenues for understanding the universe at its most fundamental level. It's a theory that pushes the boundaries of our imagination, inviting us to consider a cosmos far richer and more complex than we ever imagined. And with that, we've only just begun to unravel the mysteries of string theory. Next, we'll explore another mind-bending idea, the holographic principle, which suggests that our universe might be a projection of information encoded on a distant boundary. Stay tuned. Now, let's dive into a concept that sounds like it's straight out of science fiction, but is deeply rooted in the science of black holes and quantum gravity, the holographic principle. This idea proposes something truly mind-blowing, that all the information about our three-dimensional universe could be encoded on a two-dimensional surface, like a cosmic hologram. Imagine the entire universe as a projection, with everything we see, feel, and experience being a kind of shadow cast by information stored on a distant boundary. It's a radical rethinking of how we perceive reality. The holographic principle has its origins in the study of black holes, specifically in the work of physicist Jacob Bekenstein and later Stephen Hawking. They discovered that the entropy, or the amount of information contained within a black hole, is proportional to the area of its event horizon, not its volume. This was a groundbreaking insight because it suggested that the information about everything that falls into a black hole isn't lost but is somehow encoded on its surface. This idea was later expanded by physicists like Gerard T. Hooft and Leonard Susskind, who proposed that this principle might apply not just to black holes but to the entire universe. So, what does this mean for quantum gravity and spacetime? If the holographic principle is correct, it implies that spacetime itself might not be fundamental. Instead, it could emerge from the interactions of quantum information encoded on a lower dimensional surface. This challenges our traditional view of the universe as a smooth, continuous fabric, and suggests that spacetime might be more like a pixelated image, with each pixel representing a tiny piece of information. It's a concept that bridges the gap between quantum mechanics and gravity, offering a new way to think about how the universe works at its most fundamental level. The implications of the holographic principle are vast. It could help resolve some of the biggest puzzles in physics, like the black hole information paradox, which questions what happens to information that falls into a black hole. If information is preserved on the event horizon, as the holographic principle suggests, it could mean that nothing is truly lost, just transformed. This idea also opens up new possibilities for understanding the nature of spacetime itself, hinting that our universe might be far more interconnected and information-driven than we ever imagined. As we continue to explore the mysteries of quantum gravity, the holographic principle stands as a bold and imaginative framework that challenges our understanding of reality. Next, we'll turn our attention to another intriguing approach, causal dynamical triangulations, which reimagines spacetime as a collection of discrete building blocks. Stay with us as we uncover more about this fascinating theory. Now, let's shift our focus to a theory that takes a completely different approach to understanding spacetime: causal dynamical triangulations. This theory reimagines the fabric of the universe not as a smooth, continuous surface, but as a collection of tiny, discrete building blocks. Think of it like constructing a universe out of microscopic Lego pieces, where each piece represents a small chunk of spacetime. This approach offers a fresh perspective on quantum gravity, one that avoids the pitfalls of singularities like the Big Bang. At its core, causal dynamical triangulations rely on a mathematical framework that breaks spacetime into simple geometric shapes, typically triangles or tetrahedrons. These shapes are then connected in a way that respects causality, meaning that cause and effect are preserved, ensuring that events unfold in a logical sequence. This discrete structure allows physicists to model the universe without running into the infinite densities and breakdowns of physics that occur in singularities. It's like smoothing out the wrinkles in spacetime by giving it a pixelated yet orderly structure. One of the most intriguing aspects of this theory is how it handles the Big Bang. In traditional models, the Big Bang represents a point where the laws of physics as we know them cease to apply. But in causal dynamical triangulations, the universe doesn't collapse into a singularity. Instead, it transitions smoothly from one state to another, avoiding the infinite densities that plague other theories. This opens up the possibility of a universe that has always existed in some form, even before what we call the Big Bang. The mathematical foundations of this theory are rooted in a branch of physics known as lattice quantum gravity. By treating spacetime as a lattice of discrete points, physicists can perform calculations that would be impossible in a continuous framework. This approach has led to some fascinating insights, such as the idea that spacetime might have a minimum length scale, beyond which the concept of distance loses meaning. It's a radical departure from our everyday experience, but one that could hold the key to unifying quantum mechanics and gravity. As we explore causal dynamical triangulations, it's clear that this theory offers a unique and compelling way to think about the universe. By breaking spacetime into its smallest components, it provides a new lens through which we can examine the mysteries of quantum gravity. Next, we'll delve into another groundbreaking idea, asymptotic safety in quantum gravity, which suggests that gravity might become predictable at extremely high energies. Stay with us as we continue to unravel the secrets of the cosmos. Now, let's turn our attention to a theory that flips the script on how we think about gravity at its most extreme scales, asymptotic safety in quantum gravity. This idea suggests that gravity, which seems so unruly and unpredictable at high energies, might actually settle into a predictable pattern, a kind of cosmic calm after the storm. It's like discovering that a wild, untamed river eventually flows into a serene lake, no matter how turbulent its journey. This theory offers a tantalizing possibility that we might not need entirely new physics to unify quantum mechanics and general relativity. Instead, gravity itself could hold the key to its own unification. At the heart of asymptotic safety is the idea that gravity becomes safe at extremely high energies. In other words, instead of spiraling into chaos or breaking down entirely, gravity reaches a fixed point where its behavior becomes predictable and well-defined. This fixed point acts like a kind of anchor, ensuring that gravity remains stable even in the most extreme conditions, such as those found near the Big Bang or inside black holes. It's a bold claim, but one that could simplify our understanding of the universe by showing that gravity and quantum mechanics aren't as incompatible as they seem. The concept of asymptotic safety was first proposed by physicist Steven Weinberg in the late 1970s, and it has since gained traction as a promising avenue for quantum gravity research. Unlike other theories that require exotic new particles or dimensions, asymptotic safety relies on the properties of gravity itself. It suggests that the equations governing gravity might have a hidden symmetry or structure that becomes apparent only at very high energies. This symmetry could act as a bridge, connecting the quantum world to the realm of general relativity without the need for additional forces or particles. One of the most exciting implications of asymptotic safety is its potential to resolve some of the most stubborn problems in physics. For example, it could provide a natural explanation for why the cosmological constant, the mysterious energy driving the universe's accelerated expansion is so small. It might also shed light on the nature of singularities, those points where the laws of physics seem to break down. If gravity becomes predictable at high energies, then singularities might not be the dead ends we once thought they were. Instead, they could be gateways to new phases of the universe where the rules of physics take on a different form. As we explore asymptotic safety, it's clear that this theory offers a fresh and elegant approach to quantum gravity. By focusing on the inherent properties of gravity, it sidesteps the need for radical new physics and instead builds on the foundations we already have. It's a reminder that sometimes the answers we seek are hidden in plain sight, waiting for us to see them from the right angle. Next, we'll dive into another fascinating idea, emergent gravity, which suggests that gravity might not be a fundamental force at all. Stay tuned as we continue to uncover the secrets of the cosmos. Now, let's shift gears and explore a theory that challenges one of the most fundamental assumptions in physics, the idea that gravity might not be a fundamental force at all. This is the concept of emergent gravity, a fascinating perspective that suggests gravity isn't something inherent to the fabric of the universe, but rather something that arises from more basic quantum processes. It's like realizing that the waves on the ocean aren't the ocean itself, they're just a byproduct of deeper, unseen forces at work. At the forefront of this idea is physicist Erik Verland, who proposed a groundbreaking theory called entropic gravity. Verland's work suggests that gravity isn't a force in the traditional sense, but rather an emergent phenomenon, much like temperature or pressure. In this view, gravity emerges from the way information is distributed and processed in the universe. Imagine the universe as a vast, interconnected network, where the flow of information creates the illusion of a force pulling objects together. It's a radical rethinking of what gravity really is, and it has profound implications for our understanding of the cosmos. One of the most intriguing aspects of entropic gravity is its potential to explain dark matter and dark energy, two of the biggest mysteries in modern physics. Dark matter, which makes up about 27% of the universe, is thought to be an invisible substance that exerts gravitational pull but doesn't interact with light. Dark energy, on the other hand, is the mysterious force driving the accelerated expansion of the universe. Verland's theory suggests that these phenomena might not require new, exotic particles or fields. Instead, they could be natural consequences of the way gravity emerges from quantum information. In other words, what we call dark matter and dark energy might just be side effects of the universe's underlying information structure. To understand this better, think of the universe as a hologram. In a hologram, a three-dimensional image is encoded on a two-dimensional surface. Similarly, Verland's theory suggests that the information about the universe's gravitational field is encoded on its boundaries. This idea ties back to the holographic principle, which we discussed earlier, and shows how emergent gravity could be part of a larger framework that unifies quantum mechanics and general relativity. It's a bold and elegant idea, but one that's still being tested and refined. Emergent gravity also raises questions about the nature of spacetime itself. If gravity isn't fundamental, then spacetime might not be either. Instead, spacetime could be a kind of emergent structure, built up from the interactions of more basic quantum components. This would mean that the smooth, continuous spacetime we experience in everyday life is just an approximation, a kind of cosmic illusion created by the underlying quantum reality. It's a mind-bending concept, but one that could revolutionize our understanding of the universe. As we wrap up our exploration of emergent gravity, it's clear that this theory offers a fresh and exciting perspective on one of the most fundamental forces in nature. By reimagining gravity as an emergent phenomenon, it opens up new possibilities for solving some of the deepest mysteries in physics. Next, we'll dive into another intriguing approach, causal sets, which model spacetime as a collection of discrete events. Stay with us as we continue to unravel the secrets of quantum gravity. Now, let's take a step into a world where spacetime isn't smooth and continuous, but instead made up of tiny, discrete building blocks. This is the core idea behind the causal set approach, a fascinating theory that reimagines the very fabric of the universe. Unlike the smooth, flowing spacetime we're used to in Einstein's general relativity, causal sets propose that spacetime is fundamentally made up of individual events connected by a web of cause and effect relationships. Think of it like a cosmic tapestry where each thread represents a moment in time, and the way they're woven together creates the structure of reality. At the heart of this theory is the idea that spacetime isn't a continuous fabric but rather a collection of discrete points or events with a clear causal order. These events are linked in such a way that if one event can influence another, there's a direct connection between them. This causal structure is what gives spacetime its shape and direction, much like how the sequence of frames in a movie creates the illusion of motion. By breaking spacetime down into these discrete events, the causal set approach offers a way to address one of the biggest challenges in physics, the continuum problem. The continuum problem arises because in classical physics, spacetime is treated as smooth and infinitely divisible. But when we try to combine this idea with quantum mechanics, things start to break down. Quantum mechanics tells us that certain quantities, like energy, come in discrete packets, not continuous flows. So how can spacetime be both smooth and discrete at the same time? The causal set approach provides a potential solution by suggesting that spacetime itself is fundamentally discrete, with a finite number of events at the smallest scales. This eliminates the need for infinite divisibility and provides a more natural framework for combining quantum mechanics and gravity. One of the most exciting implications of causal sets is their potential to resolve singularities, those points in spacetime where the laws of physics seem to break down, like at the center of a black hole or the moment of the Big Bang. In general relativity, singularities are places where spacetime curvature becomes infinite, and our equations stop making sense. But in the causal set approach, spacetime is made up of discrete events, so there's no such thing as infinite curvature. Instead, singularities might simply be places where the causal structure becomes highly complex or breaks down in a way that's still governed by quantum rules. This could mean that singularities aren't the end of the story, but rather gateways to new physics. To visualize this, imagine spacetime as a vast network of points, each representing a specific event. These points are connected in a way that reflects cause and effect, creating a kind of cosmic roadmap. As you zoom in, you'd see that this network isn't smooth. It's made up of individual nodes and links, like a digital image made of pixels. This discrete structure could help us understand how spacetime behaves at the smallest scales where quantum effects dominate, and provide a new way to think about the universe's most extreme environments. The causal set approach also has deep connections to other theories of quantum gravity, like loop quantum gravity and the holographic principle. For example, the idea that spacetime emerges from more fundamental structures aligns with the holographic principle's suggestion that the universe's information is encoded on its boundaries. Similarly, the discrete nature of causal sets echoes the quantized spacetime of loop quantum gravity. These connections hint at a larger framework that could one day unify our understanding of the universe. As we wrap up our exploration of causal sets, it's clear that this theory offers a bold and innovative way to rethink spacetime itself. By breaking it down into discrete events with a causal structure, it provides a fresh perspective on some of the most challenging problems in physics, from the continuum problem to the nature of singularities. Next, we'll dive into another intriguing idea, non-commutative geometry, which takes a completely different approach to redefining spacetime at the quantum level. Stay with us as we continue to unravel the mysteries of quantum gravity. Now, let's shift our focus to a theory that takes a radically different approach to redefining spacetime: non-commutative geometry. Unlike the smooth, continuous spacetime we're familiar with, this theory suggests that at the quantum level, spacetime might be better described by algebraic structures rather than traditional geometric shapes. Imagine trying to describe the universe not with the smooth curves of a sphere or the flat planes of a cube, but with the abstract language of mathematics, equations, and relationships that don't follow the usual rules of geometry. This is the essence of non-commutative geometry. At its core, non-commutative geometry challenges the idea that spacetime is a smooth manifold, the kind of structure Einstein used in his theory of general relativity. Instead, it proposes that spacetime is made up of algebraic entities where the order of operations matters. In simpler terms, think of it like this. In normal arithmetic, 2 times 3 is the same as 3 times 2. But in non-commutative geometry, the order in which you perform operations can change the outcome. This might sound abstract, but it has profound implications for how we understand the fabric of the universe. One of the key motivations behind non-commutative geometry is the need to reconcile quantum mechanics with gravity. At the Planck scale, the smallest possible scale in the universe, our classical notions of space and time break down. Quantum mechanics tells us that particles can exist in multiple states at once, and spacetime itself might be subject to similar uncertainties. Non-commutative geometry provides a framework where spacetime becomes fuzzy and uncertain at these tiny scales, much like the behavior of particles in quantum mechanics. This fuzziness isn't a flaw but a feature, offering a way to describe the quantum nature of spacetime without running into the infinities that plague classical theories. One of the most intriguing aspects of this theory is its potential to explain phenomena like the uncertainty principle in quantum mechanics. Just as particles can't have both a precise position and momentum at the same time, spacetime in non-commutative geometry might not have a precise location or structure at the smallest scales. Instead, it's defined by probabilities and relationships, creating a kind of quantum foam where spacetime fluctuates unpredictably. This idea aligns with other quantum gravity theories like loop quantum gravity and the holographic principle, suggesting that spacetime might emerge from more fundamental, non-geometric structures. Non-commutative geometry also has implications for the nature of singularities, those points where the laws of physics seem to break down. In classical general relativity, singularities are places of infinite density and curvature, like the center of a black hole. But in non-commutative geometry, the fuzziness of spacetime at the quantum level could prevent these infinities from forming. Instead of a singularity, we might find a region where spacetime becomes so uncertain that it's impossible to define a single point of infinite density. This could open the door to new ways of understanding black holes and the Big Bang, where the usual rules of physics no longer apply. To put it another way, non-commutative geometry offers a way to think about spacetime that's fundamentally different from anything we've seen before. It's not about smooth curves or flat planes, but about relationships and probabilities, where the very fabric of the universe is defined by the interactions between its most basic elements. This approach could help us bridge the gap between quantum mechanics and gravity, providing a new perspective on some of the most profound questions in physics. As we move forward, we'll explore another fascinating idea: quantum graphity, a theory that suggests spacetime might emerge from a network of quantum interactions. Stay with us as we continue to uncover the mysteries of quantum gravity and the universe itself. Now, let's turn our attention to a theory that reimagines spacetime in a way that feels almost like a cosmic puzzle: quantum graphity. This fascinating idea suggests that spacetime isn't a smooth, continuous fabric, but rather emerges from a vast network of quantum interactions, much like how a spider's web is built from countless interconnected threads. At its heart, quantum graphity proposes that the universe's structure is more like a dynamic, evolving graph, a mathematical network where points are connected by lines, than the smooth, geometric space we're used to. To understand this better, think of spacetime as a kind of cosmic internet. Just as the internet is made up of countless nodes and connections, quantum graphity suggests that spacetime is built from a network of quantum interactions. These interactions aren't random, they follow specific rules that determine how the network evolves over time. In this view, the smooth, continuous spacetime we experience on large scales is actually an illusion, a kind of emergent property that arises from the complex web of quantum connections at the smallest scales. One of the most intriguing aspects of quantum graphity is its connection to condensed matter physics, the branch of physics that studies how particles behave in solid and liquid materials. In condensed matter systems, we often see emergent phenomena, properties that arise from the collective behavior of many particles, even though they aren't present in the individual particles themselves. For example, superconductivity, where electricity flows without resistance, is an emergent property of certain materials. Quantum graphity borrows this idea, suggesting that spacetime itself might be an emergent phenomenon arising from the collective behavior of a quantum network. This connection to condensed matter physics isn't just a neat analogy, it's a powerful tool for understanding the early universe. In the moments after the Big Bang, the universe was incredibly hot and dense, with particles and energy packed into a tiny, chaotic space. Quantum graphity proposes that during this time, the network of quantum interactions was highly disordered, like a tangled web. As the universe expanded and cooled, this network began to freeze into a more ordered structure, giving rise to the spacetime we know today. This process is similar to how water freezes into ice, transitioning from a chaotic, fluid state to a more structured, solid one. But quantum graphity doesn't just explain the early universe, it also offers insights into the nature of spacetime itself. For instance, it suggests that spacetime might not be fundamental, but rather something that emerges from deeper, more fundamental processes. This idea aligns with other quantum gravity theories, like loop quantum gravity and the holographic principle, which also propose that spacetime is not the ultimate foundation of reality, but something that arises from more basic building blocks. Another exciting implication of quantum graphity is its potential to explain the universe's large-scale structure. Just as the patterns in a spider's web depend on how the threads are connected, the structure of spacetime in quantum graphity depends on the network's configuration. This could provide a new way to understand phenomena like cosmic inflation, the rapid expansion of the universe in its earliest moments, and the formation of galaxies and other large-scale structures. As we continue to explore the mysteries of quantum graphity offers a fresh perspective on how spacetime might emerge from the quantum realm. It's a reminder that the universe's deepest secrets might not lie in the smooth, continuous fabric of spacetime, but in the intricate, interconnected web of quantum interactions that underlies it all. Next, we'll dive into twistor theory, another groundbreaking idea that redefines how we think about spacetime and its connection to quantum mechanics. Stay tuned as we unravel more of the universe's quantum mysteries. Now, shifting our focus to another groundbreaking idea, let's explore twistor theory, a fascinating approach that reimagines spacetime using the language of complex numbers. Developed by the renowned physicist Roger Penrose in the 1960s, twistor theory offers a radical new way to describe the geometry of spacetime, one that could potentially bridge the gap between quantum mechanics and gravity. At its core, twistor theory replaces the traditional coordinates of spacetime with mathematical objects called twistors. These twistors are built using complex numbers which combine real and imaginary components, allowing them to encode both the position and momentum of particles in a single, elegant framework. This approach is a dramatic departure from the way we usually think about spacetime, which relies on coordinates like length, width, height, and time. Instead, twister theory suggests that the fundamental building blocks of the universe might not be points in space, but rather these twisters, which describe the relationships between particles and their motion. One of the most compelling aspects of twister theory is its ability to simplify some of the most complex problems in physics. For example, it provides a powerful tool for calculating particle interactions, particularly in the realm of quantum field theory. By reformulating these interactions in terms of twisters, physicists can often avoid the cumbersome calculations that arise in traditional approaches. This has made twister theory especially useful in studying scattering amplitudes, which describe how particles interact and exchange energy during collisions. But twister theory isn't just a mathematical shortcut. It also offers profound insights into the nature of spacetime itself. In this framework, spacetime isn't a fixed, pre-existing stage where events unfold. Instead, it emerges from the relationships encoded in twisters. This idea aligns with other quantum gravity theories, like loop quantum gravity and the holographic principle, which also suggest that spacetime is not fundamental but something that arises from deeper, more basic structures. Roger Penrose's work on twister theory was initially inspired by his desire to unify quantum mechanics and general relativity, two pillars of modern physics that have proven notoriously difficult to reconcile. While twister theory hasn't yet achieved this unification, it has provided a rich mathematical framework that continues to inspire new research. For instance, it has found applications in string theory and has even been used to explore the behavior of black holes and gravitational waves. One of the most intriguing possibilities of twister theory is its potential to explain the nature of quantum gravity. By describing spacetime in terms of twisters, the theory offers a way to quantize gravity without running into the infinities that plague other approaches. This could provide a path toward a unified theory of everything, one that seamlessly combines the quantum world with the gravitational forces that shape the cosmos. As we continue to explore the mysteries of the universe, twister theory reminds us that sometimes the most profound insights come from rethinking the very foundations of our understanding. By shifting our perspective from points in space to the intricate relationships encoded in twisters, we may uncover new ways to describe the fabric of reality itself. Next, we'll delve into the fascinating connection between black holes, thermodynamics, and quantum gravity, where some of the universe's most perplexing puzzles await. Stay with us as we journey deeper into the quantum realm, now turning our attention to one of the most enigmatic phenomena in the universe. Let's explore the fascinating intersection of black holes, thermodynamics, and quantum gravity. Black holes, those cosmic vacuum cleaners, are not just regions of immense gravitational pull. They are also laboratories for testing the limits of our understanding of physics. At the heart of this exploration lies a surprising connection between black holes and the laws of thermodynamics, a relationship that has profound implications for quantum gravity. The story begins with Stephen Hawking's groundbreaking discovery in the 1970s. Black holes aren't entirely black. They emit radiation, now famously known as Hawking radiation. This radiation arises from quantum effects near the event horizon, the boundary beyond which nothing, not even light, can escape. According to quantum mechanics, pairs of particles and antiparticles constantly pop in and out of existence in empty space. Near a black hole's event horizon, one of these particles can fall into the black hole while the other escapes, carrying away energy. Over time, this process causes the black hole to lose mass and eventually evaporate. This revelation was revolutionary because it suggested that black holes have a temperature and, by extension, entropy, a measure of disorder or information content. This discovery tied black holes directly to the laws of thermodynamics. Just as a hot cup of coffee radiates heat and cools down, black holes radiate energy and lose mass. But here's where things get even more intriguing. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This idea, known as the Bekenstein-Hawking entropy, hints at a deep connection between gravity, quantum mechanics, and information. It suggests that all the information about what falls into a black hole might somehow be encoded on its surface, a concept that resonates with the holographic principle we discussed earlier. However, this connection also leads to one of the most perplexing puzzles in modern physics, the black hole information paradox. According to quantum mechanics, information cannot be destroyed. Yet, if a black hole evaporates completely through Hawking radiation, what happens to all the information about the matter that fell into it? Does it vanish, violating quantum principles, or is it somehow preserved in the radiation? This paradox has sparked decades of debate and remains one of the biggest challenges in our quest to unify quantum mechanics and gravity. Black holes also challenge our understanding of spacetime itself. Near the singularity at the center of a black hole, where gravity becomes infinitely strong, the fabric of spacetime breaks down. General relativity, which describes gravity as the curvature of spacetime, fails to explain what happens in such extreme conditions. This is where quantum gravity theories come into play, offering potential frameworks to describe these regions. For instance, loop quantum gravity suggests that spacetime might be discrete at the smallest scales, preventing the formation of singularities. Similarly, string theory proposes that black holes might be composed of fundamental strings or branes, offering new ways to resolve these paradoxes. The study of black hole thermodynamics has not only deepened our understanding of these cosmic objects, but also provided crucial insights into the nature of quantum gravity. It has shown us that black holes are not just gravitational monsters, but also windows into the fundamental laws of the universe. As we continue to probe their mysteries, we may uncover answers to some of the most profound questions in physics, from the fate of information to the true nature of spacetime. With this in mind, let's move forward to another intriguing concept, the anti-de Sitter/conformal field theory correspondence, a duality that bridges the gap between gravity in higher dimensions and quantum field theory on a boundary. This idea takes us even deeper into the quantum realm, where the universe's secrets continue to unfold. Stay with us as we unravel more of these cosmic puzzles. Now, let's dive into one of the most mind-bending ideas in modern physics, the anti-de Sitter/conformal field theory correspondence, often abbreviated as ADS/CFT. This concept is a cornerstone of theoretical physics, offering a profound connection between gravity and quantum mechanics. At its core, ADS/CFT proposes a duality, a kind of mathematical equivalence between two seemingly unrelated frameworks, gravity in a higher dimensional space and a quantum field theory living on the boundary of that space. To unpack this, imagine a universe with an extra-spatial dimension, described by a type of spacetime called anti-de Sitter space, or AD-S for short. In this higher dimensional world, gravity behaves according to Einstein's general relativity. But here's the twist. The physics of this higher dimensional gravity can be completely described by a quantum field theory operating on the lower dimensional boundary of this space. This boundary theory is a conformal field theory, or CFT, which is a special kind of quantum field theory that remains unchanged under certain transformations like scaling or rotations. This duality is often described using the analogy of a hologram. Just as a two-dimensional holographic image can encode all the information of a three-dimensional object, the quantum field theory on the boundary encodes all the information about the higher dimensional gravitational theory. This is why AD-S/CFT is closely tied to the holographic principle, which we explored earlier. It suggests that the universe might fundamentally be a kind of hologram, with all the information about its structure and dynamics encoded on a lower dimensional surface. The implications of AD-S/CFT are staggering. For one, it provides a powerful tool for studying quantum gravity. By translating problems in higher dimensional gravity into problems in quantum field theory, physicists can tackle questions that were previously out of reach. For example, ADS/CFT has been used to explore the behavior of black holes, the nature of spacetime singularities, and even the properties of quark-gluon plasma, a state of matter that existed just after the Big Bang. But ADS/CFT isn't just a mathematical curiosity, it's a potential roadmap to unifying quantum mechanics and gravity. By showing how gravity can emerge from a quantum system, it offers a glimpse into how these two pillars of physics might fit together. It also raises profound questions about the nature of reality. If the universe is truly holographic, what does that mean for our understanding of space, time, and information? As we continue to explore the mysteries of quantum gravity, the ADS/CFT correspondence stands as a testament to the power of theoretical physics to reveal hidden connections in the fabric of the universe. And with that, let's turn our attention to another fascinating concept, quantum foam, where spacetime itself becomes turbulent at the smallest scales. Stay tuned as we venture deeper into the quantum realm. Now, let's shift our focus to a concept that takes us even deeper into the quantum realm, quantum foam. Picture spacetime not as the smooth, continuous fabric we often imagine, but as a turbulent, frothy sea at the tiniest scales. This is the essence of quantum foam, a term coined by physicist John Wheeler in the 1950s to describe the chaotic nature of spacetime at the Planck scale, where quantum effects dominate. At these unimaginably small distances, around 1/1,000,000,000 of a trillionth of the width of an atom, spacetime is no longer stable. Instead, it fluctuates wildly, bubbling and churning like foam on the surface of the ocean. These fluctuations are so intense that the very structure of spacetime becomes uncertain, with tiny regions constantly forming and dissolving. This turbulence arises from the inherent uncertainty of quantum mechanics, where particles and energy can pop in and out of existence in what we call quantum fluctuations. John Wheeler proposed this idea as a way to reconcile the smooth spacetime of general relativity with the unpredictable nature of quantum mechanics. In his view, the smooth spacetime we observe on larger scales is just an average of this underlying chaos. It's like looking at the surface of a calm lake from a distance. It appears smooth, but up close you'd see ripples and waves. Similarly, on the Planck scale, spacetime is anything but smooth. The implications of quantum foam are profound. For one, it challenges our understanding of the very fabric of reality. If spacetime is turbulent at the smallest scales, what does that mean for concepts like distance, time, and causality? Could these fluctuations allow for phenomena like wormholes or even shortcuts through spacetime? While these ideas remain speculative, they highlight how quantum foam forces us to rethink the nature of the universe. Moreover, quantum foam has implications for the search for a theory of quantum gravity. If spacetime itself is fluctuating, then any theory attempting to unify quantum mechanics and gravity must account for this chaotic behavior. This makes quantum foam a key area of study for physicists exploring the boundaries of our understanding. As we ponder the turbulent nature of spacetime, we're reminded just how strange and unpredictable the quantum world can be. And with that, let's move on to another intriguing idea: spin networks, the mathematical structures that loop quantum gravity uses to describe spacetime at its most fundamental level. Stay with us as we continue to unravel the mysteries of the universe. Now, let's dive into the fascinating world of spin networks, a concept that takes us to the very heart of loop quantum gravity. Imagine spacetime not as a smooth, continuous fabric, but as a web of interconnected nodes and links, a kind of cosmic tapestry woven from the threads of quantum geometry. This is the essence of spin networks, mathematical structures that provide a radically new way to describe spacetime at its most fundamental level. Spin networks were first introduced by physicist Roger Penrose in the 1970s, but they found their true home in loop quantum gravity, a theory developed by Carlo Rovelli and Smolin. In this framework, spacetime is not infinitely divisible but is instead made up of discrete quantized units. These units are represented by the nodes of a spin network, while the links between them describe how these units are connected. Think of it like a cosmic Lego set where each block represents a tiny piece of spacetime, and the way they fit together determines the structure of the universe. The spin in spin networks refers to the quantum states associated with these nodes and links. Just as particles like electrons have spin, the nodes and links in a spin network carry quantum information that encodes the geometry of spacetime. This means that the very fabric of the universe is built from these quantum building blocks, with each node representing a tiny volume of space and each link representing the area between them. It's a profound shift from the smooth, continuous spacetime of general relativity to a pixelated, quantum version of reality. One of the most exciting aspects of spin networks is how they quantize geometry. In classical physics, space and time are continuous, meaning you can divide them infinitely. But in loop quantum gravity, there's a smallest possible unit of space, a kind of quantum pixel. This has huge implications for our understanding of the universe, especially when it comes to phenomena like black holes and the Big Bang. For instance, the singularity at the center of a black hole, where classical physics breaks down, might be replaced by a dense tangle of spin networks, avoiding the infinite densities predicted by general relativity. Spin networks also offer a unique perspective on the nature of quantum states. In this framework, the quantum states of spacetime itself are described by the configurations of these networks. This means that the geometry of the universe is not fixed but is constantly evolving, with spin networks changing and rearranging over time. It's a dynamic, ever-shifting picture of reality that challenges our classical notions of space and time. As we explore spin networks, we're reminded just how deeply quantum mechanics reshapes our understanding of the universe. These structures not only provide a new way to describe spacetime, but also open up exciting possibilities for unifying quantum mechanics and gravity. And with that, let's turn our attention to another intriguing idea: the role of quantum entanglement in theories of quantum gravity. Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's shift our focus to one of the most mind-bending concepts in modern physics: the role of quantum entanglement in theories of quantum gravity. Quantum entanglement, often called spooky action at a distance by Einstein, is a phenomenon where particles become so deeply connected that the state of one instantly influences the state of another, no matter how far apart they are. But what does this have to do with gravity and the fabric of spacetime? As it turns out, quite a lot. In recent years, physicists have discovered that entanglement isn't just a quirky feature of quantum mechanics. It might actually be the glue that holds spacetime itself together. This idea stems from the holographic principle, which suggests that the information about a volume of space can be encoded on its boundary. Entanglement entropy, a measure of how entangled particles are, plays a key role here. It turns out that the amount of entanglement between particles is directly related to the geometry of spacetime. In other words, the way particles are entangled could determine the shape and structure of the universe. One of the most striking examples of this connection comes from black holes. When particles fall into a black hole, they become entangled with the black hole's interior. But according to the laws of quantum mechanics, information can't be destroyed. This creates a paradox. How can the information about the particles be preserved if they're trapped inside the black hole? The answer might lie in entanglement. Some theories suggest that the information is encoded in the entanglement between particles inside the black hole and those outside, effectively linking the black hole's interior to its exterior through a web of quantum connections. This idea has led to the concept of entanglement bridges, which some physicists believe could replace the traditional notion of spacetime. Instead of thinking of space as a smooth, continuous fabric, we might need to think of it as a network of entangled particles, with the strength of their entanglement determining the geometry of the universe. This could even provide a way to unify quantum mechanics and gravity, two theories that have stubbornly resisted reconciliation for over a century, but the implications don't stop there. Entanglement entropy also offers new insights into the nature of black holes. For instance, it might help explain the mysterious phenomenon of Hawking radiation, where black holes slowly lose energy and evaporate over time. By studying how entanglement changes as a black hole evaporates, physicists hope to solve the black hole information paradox and gain a deeper understanding of how quantum gravity works. As we explore the connection between entanglement and quantum gravity, we're reminded just how interconnected the universe truly is. From the smallest particles to the largest black holes, entanglement weaves a complex web that might hold the key to understanding the very fabric of reality. And with that, let's move on to another fascinating idea: brain-world scenarios where our universe might be just one layer in a higher dimensional reality. Stay tuned as we continue to unravel the mysteries of the cosmos. Now, let's step into a realm that feels like it's straight out of science fiction brain-world scenarios. Imagine our universe not as a standalone entity, but as a membrane or brain, floating within a higher dimensional space. This idea, rooted in string theory, suggests that the three-dimensional world we experience is just one layer in a much larger, multidimensional reality. But what does this mean for quantum gravity and the fundamental forces that shape our universe? In brain-world models, our universe is like a sheet of paper suspended in a higher dimensional bulk. While we're confined to the brain, gravity, unlike other forces, can leak into the bulk. This could explain why gravity is so much weaker than the other fundamental forces. It's not confined to our brain but spread out across the extra dimensions. This idea offers a potential solution to the hierarchy problem in particle physics, which asks why gravity is so much feebler compared to forces like electromagnetism or the strong nuclear force. If gravity is diluted across higher dimensions, its apparent weakness in our universe makes sense, but the implications go even deeper. Brain-world scenarios could also shed light on the nature of quantum gravity. If gravity operates in higher dimensions, it might behave differently at extremely small scales, potentially bridging the gap between quantum mechanics and general relativity. Some theories even suggest that black holes could be higher dimensional objects with their intense gravitational fields extending into the bulk. This could provide new ways to test quantum gravity experimentally, as higher dimensional effects might leave subtle traces in our universe. One of the most intriguing aspects of brain-world models is the possibility of parallel universes. If multiple brains exist in the bulk, each could host its own universe with different physical laws. Collisions between brains could even explain cosmic events like the Big Bang, offering a radical new perspective on the origins of our universe. While these ideas are still speculative, they highlight how brain-world scenarios challenge our understanding of reality and open up exciting new avenues for exploration. As we wrap up this dive into brain worlds, it's clear that these models aren't just theoretical curiosities. They could hold the key to solving some of the biggest puzzles in physics. From the hierarchy problem to the nature of quantum gravity, brain worlds offer a fresh lens through which to view the cosmos. And with that, let's turn our attention to another groundbreaking idea, quantum cosmology, where we'll explore how quantum mechanics applies to the universe as a whole. Stay tuned as we continue to unravel the mysteries of quantum gravity. Now, let's shift our focus to a theory that takes quantum mechanics to the grandest scale imaginable: quantum cosmology. This fascinating field applies the principles of quantum mechanics not just to particles or atoms, but to the entire universe itself. It's a bold attempt to understand the cosmos through the lens of quantum theory, and it leads us to some truly mind-bending ideas about the nature of reality. At the heart of quantum cosmology lies the Wheeler-DeWitt equation, a groundbreaking concept developed by physicists John Wheeler and Bryce DeWitt. This equation is often described as the quantum version of Einstein's equations of general relativity. Instead of describing the universe as a smooth, continuous fabric of spacetime, the Wheeler-DeWitt equation treats the universe as a quantum system, where its properties can exist in multiple states simultaneously, just like particles in a quantum superposition. This means the universe itself could have been in a superposition of states at its very beginning, challenging our classical understanding of the Big Bang. One of the most intriguing implications of the Wheeler-DeWitt equation is the idea of a timeless universe. In this framework, time as we know it might not be a fundamental feature of reality. Instead, it could emerge from the quantum interactions of the universe's components. This raises profound questions. If time isn't fundamental, how do we explain the arrow of time or the apparent flow from past to future? Quantum cosmology suggests that time might be an illusion, a byproduct of the universe's quantum structure. Quantum cosmology also opens the door to multiverse theories. If the universe began in a quantum superposition, it's possible that multiple universes could have emerged from that initial state, each with its own set of physical laws. This idea aligns with the concept of the quantum multiverse, where every possible outcome of a quantum event spawns a new universe. While this might sound like science fiction, it's a serious area of research that could explain why our universe has the specific properties it does. It might just be one of countless possibilities. But quantum cosmology isn't just about abstract ideas. It has practical implications for understanding the early universe. By applying quantum mechanics to the Big Bang, physicists hope to resolve some of the paradoxes that arise when classical physics breaks down at the singularity. For instance, quantum effects could have smoothed out the extreme conditions of the early universe, avoiding the infinite densities predicted by classical theories. This could provide a more complete picture of how our universe began and evolved. As we explore quantum cosmology, it's clear that this theory pushes the boundaries of our understanding, blending the strange world of quantum mechanics with the vastness of the cosmos. It challenges us to rethink fundamental concepts like time, space, and the very nature of existence. And with that, let's move on to another fascinating idea, doubly special relativity, where we'll examine how modifying the rules of relativity could help us reconcile quantum mechanics and gravity. Stay with us as we continue our journey through the mysteries of quantum gravity. Now, let's turn our attention to a theory that reimagines one of the cornerstones of modern physics, special relativity. This is doubly special relativity, a bold idea that takes Einstein's groundbreaking work and tweaks it to include a minimum length scale, offering a fresh perspective on how quantum mechanics and gravity might coexist at extreme energies. At its core, doubly special relativity builds on Einstein's theory of special relativity, which revolutionized our understanding of space and time by showing that they are interwoven into a single fabric called spacetime. But here's the twist. Doubly special relativity introduces a new fundamental constant, a minimum length scale, often linked to the Planck length. This tiny scale, about 1/trillionth of a trillionth the size of an atom, represents the smallest possible distance in the universe. By incorporating this limit, doubly special relativity suggests that spacetime might not be as smooth and continuous as we once thought. Instead, it could have a granular structure at the smallest scales, much like pixels on a screen. This idea has profound implications for how we understand high-energy phenomena, such as those near black holes or during the Big Bang. In these extreme environments, the effects of quantum gravity become significant and classical physics breaks down. Doubly special relativity proposes that at these energies, the rules of spacetime itself might change. For example, the speed of light, which is a constant in Einstein's theory, could vary slightly at ultra-high energies. This could help bridge the gap between quantum mechanics, which governs the very small, and gravity, which dominates the very large. One of the most exciting aspects of doubly special relativity is its potential to resolve some of the paradoxes that arise when trying to merge quantum mechanics and gravity. For instance, it could provide a way to avoid the infinite densities predicted by classical theories at the center of black holes or during the Big Bang. By introducing a minimum length scale, the theory suggests that spacetime might self-regulate at these extreme conditions, preventing the breakdown of physics as we know it. But doubly special relativity isn't just about solving theoretical problems. It also challenges our understanding of fundamental concepts like energy and momentum. In this framework, the way particles carry energy and momentum could change at high energies, leading to new predictions that could be tested in experiments. While these effects are incredibly subtle and difficult to detect, they offer a tantalizing possibility. We might one day find evidence of quantum gravity in the behavior of high-energy particles. As we explore doubly special relativity, it's clear that this theory pushes the boundaries of our understanding, offering a new way to think about the universe's most extreme environments. It challenges us to reconsider the very fabric of spacetime and how it behaves under conditions we've yet to fully comprehend. And with that, let's move on to another intriguing idea, quantum gravity and the multiverse, where we'll explore how these theories intersect with the concept of parallel universes. Stay with us as we continue unraveling the mysteries of quantum gravity. Now, let's venture into a realm where quantum gravity meets one of the most mind-bending ideas in modern physics, the multiverse. This is where the fabric of reality stretches beyond our universe, suggesting the existence of parallel worlds, each with its own unique set of physical laws and possibilities. Quantum gravity theories play a crucial role in shaping this concept, offering a framework to explore how multiple universes might coexist and interact. At the heart of the multiverse idea is the notion that our universe is just one of many, perhaps even an infinite number of universes. These parallel worlds could exist alongside ours, separated by dimensions we can't perceive or embedded within a larger cosmic structure. Quantum gravity theories such as string theory and loop quantum gravity provide the tools to investigate how these universes might form and evolve. For instance, string theory suggests that our universe could be one of many branes floating in a higher dimensional space, while loop quantum gravity explores how spacetime itself might branch into multiple realities. One of the most fascinating implications of the multiverse is the idea that the laws of physics we observe in our universe might not be universal. In other words, the constants and forces that govern our reality, like the speed of light or the strength of gravity, could vary in other universes. This raises profound questions about the nature of reality. Are the laws of physics we see simply a matter of chance, or is there a deeper reason why they are the way they are? Quantum gravity theories attempt to address these questions by examining how different universes might emerge from the same underlying quantum processes. The multiverse also intersects with quantum gravity in the context of black holes and the Big Bang. Some theories propose that black holes could act as gateways to other universes, with their intense gravitational fields warping spacetime to create new cosmic realms. Similarly, the Big Bang might not have been a singular event, but rather one of many bangs occurring across a vast multiverse. These ideas challenge our understanding of the universe's origins and suggest that our reality might be just one piece of a much larger puzzle. But the multiverse isn't just a theoretical playground. It has practical implications for our understanding of quantum gravity. For example, if multiple universes exist, they could influence each other through quantum entanglement or other subtle interactions. This could provide a way to test the predictions of quantum gravity theories, as the effects of these interactions might leave detectable traces in our universe. While such experiments are still far beyond our current capabilities, they offer a tantalizing glimpse into how we might one day explore the multiverse. As we ponder the multiverse, it's clear that this concept pushes the boundaries of our imagination, challenging us to rethink what we know about reality. Quantum gravity theories provide a lens through which we can explore these possibilities, offering insights into how multiple universes might coexist and interact. And with that, let's turn our attention to another intriguing question: the role of time in quantum gravity theories, where we'll explore how time itself might behave in the quantum realm. Stay with us as we continue our journey through the mysteries of quantum gravity. Now, let's shift our focus to a concept that's as fundamental as it is mysterious: time. In the realm of quantum gravity, time takes on a whole new dimension, challenging our everyday understanding of how it flows and functions. Unlike in classical physics, where time is a steady, unchanging backdrop, quantum gravity theories suggest that time might behave in ways that defy intuition, or perhaps not exist as we know it at all. One of the most striking ideas in this area is the concept of timelessness. In some quantum gravity theories, time isn't a fundamental feature of the universe, but rather an emergent property that arises from more basic quantum processes. This idea is encapsulated in the Wheeler-DeWitt equation, a cornerstone of quantum cosmology. Proposed by physicists John Wheeler and Bryce DeWitt, this equation describes the universe without explicit reference to time. Instead, it treats the universe as a static, timeless entity, where all possible configurations of space and matter coexist simultaneously. This might sound bizarre, but it raises profound questions about what time really is. Is it an illusion, a byproduct of deeper quantum interactions, or something else entirely? The implications of timelessness are mind-bending. If time isn't fundamental, then our experience of past, present, and future might be a kind of cosmic trick, a way for our brains to make sense of a universe that exists all at once. This idea aligns with the block universe theory, which suggests that time is like a frozen river, with every moment past, present, and future existing eternally. Quantum gravity theories like loop, quantum gravity, and string theory explore how this timeless framework might emerge from the quantum fabric of spacetime. But timelessness isn't the only way quantum gravity redefines time. Some theories propose that time might flow differently at the quantum level, or even that it could be quantized, broken into discrete chunks, much like space. In loop quantum gravity, for example, spacetime is made up of tiny, indivisible loops, and time itself might be granular rather than continuous. This could mean that the smooth flow of time we experience is an approximation, a kind of cosmic averaging of these tiny quantum fluctuations. Another fascinating angle is the role of time in black holes and the early universe. Near the singularity of a black hole, or at the moment of the Big Bang, the extreme conditions might cause time to behave in ways we can't yet fully understand. Some theories suggest that time could slow down, stop, or even reverse in these extreme environments. This challenges our understanding of causality, the idea that cause must always precede effect, and opens up the possibility of exotic phenomena like closed time-like curves where time loops back on itself. So, what does all this mean for our understanding of time? Quantum gravity theories force us to rethink time as something far more complex and dynamic than the ticking of a clock. Whether time is emergent, quantized, or even an illusion, these ideas push the boundaries of our imagination and challenge us to see the universe in a new light. And as we continue to explore these theories, we're reminded that time, like the universe itself, is full of mysteries waiting to be unraveled. With that, let's move forward to another intriguing question: how quantum gravity intersects with one of the universe's greatest enigmas, dark energy. Stay tuned as we dive deeper into the quantum mysteries that shape our cosmos. Now, let's turn our attention to one of the most puzzling forces in the universe, dark energy. This mysterious energy is thought to be responsible for the accelerated expansion of the cosmos. but its true nature remains one of the biggest questions in modern physics. Quantum gravity theories offer some intriguing possibilities for explaining dark energy, and they might even hold the key to solving the cosmological constant problem, a long-standing puzzle that has baffled scientists for decades. At the heart of the cosmological constant problem is a discrepancy between theory and observation. According to quantum field theory, the vacuum of space should be teeming with energy, so-called quantum vacuum energy. This energy arises from the constant fluctuations of particles and fields at the smallest scales. When physicists try to calculate how much energy this vacuum should contain, the numbers they get are staggeringly large, far exceeding what we observe in the universe. This mismatch is one of the most significant unsolved problems in physics, and it's where quantum gravity theories step in. One idea is that quantum gravity could provide a mechanism to cancel out or reduce the enormous predicted value of vacuum energy. In some theories, like string theory, extra dimensions or symmetries might play a role in balancing out the energy, bringing it down to the tiny value we observe. Another possibility is that quantum gravity introduces new principles that fundamentally change how we think about vacuum energy. For example, in loop quantum gravity, the discrete nature of spacetime at the smallest scales might prevent the buildup of infinite energy, offering a natural solution to the problem. But the connection between quantum gravity and dark energy goes even deeper. Some theories suggest that dark energy might not be a static force but rather a dynamic one, evolving over time. In these models, the energy density of the universe could change as spacetime itself evolves, influenced by quantum gravitational effects. This could explain why the expansion of the universe is accelerating now but might have behaved differently in the past or could change again in the future. Another fascinating angle is the idea that dark energy might be linked to the quantum structure of spacetime itself. In some quantum gravity frameworks, spacetime isn't smooth and continuous but rather made up of tiny, discrete units. These quantum fluctuations could give rise to dark energy as a kind of emergent phenomenon, a side effect of the universe's underlying quantum nature. This would mean that dark energy isn't a separate entity but an intrinsic feature of spacetime, shaped by the same quantum rules that govern everything else. So, what does all this mean for our understanding of the universe? Quantum gravity theories offer fresh perspectives on dark energy, suggesting that it might be deeply connected to the fabric of spacetime and the quantum world. While we're still far from a complete explanation, these ideas open up exciting new avenues for research and challenge us to think differently about the forces that shape our cosmos. As we continue to explore the mysteries of dark energy, quantum gravity might just be the key to unlocking one of the universe's greatest secrets. And with that, let's move on to another fascinating intersection: how quantum gravity might shed light on the nature of dark matter. Stay tuned as we dive deeper into the quantum mysteries that define our universe. Now, shifting our focus to another cosmic mystery, let's explore how quantum gravity might hold the key to understanding dark matter. While dark energy drives the universe's expansion, dark matter is the invisible force that shapes its structure, holding galaxies together and influencing their motion. Yet, despite its profound impact, dark matter remains elusive, detectable only through its gravitational effects. Could quantum gravity theories help us uncover its true nature? Let's dive in. One intriguing idea is that dark matter might not be made of particles at all, but rather emerge from the quantum structure of spacetime itself. In some quantum gravity frameworks, spacetime isn't smooth and continuous, but instead composed of tiny, discrete units. These quantum fluctuations could give rise to dark matter as an emergent phenomenon, a byproduct of the universe's underlying quantum nature. This would mean dark matter isn't a separate substance but an intrinsic feature of spacetime, shaped by the same quantum rules that govern everything else. Another possibility is that dark matter arises from interactions between quantum fields and gravity. In certain theories, such as those involving extra dimensions or modified gravity, quantum effects could create new types of particles or fields that behave like dark matter. For example, in string theory, the extra dimensions required by the theory might host particles that don't interact with light but still exert gravitational influence, making them perfect candidates for dark matter. Some researchers also suggest that dark matter could be connected to black holes or other exotic objects predicted by quantum gravity. Primordial black holes formed in the early universe could account for some or all of the dark matter we observe. These black holes would be too small to detect directly but could still exert gravitational effects on their surroundings. Alternatively, quantum gravity might predict new types of objects like quantum knots or spacetime defects that could behave like dark matter. What's fascinating is that quantum gravity doesn't just offer new candidates for dark matter. It also provides new ways to test these ideas. For instance, if dark matter is linked to quantum spacetime, its effects might leave subtle imprints on the cosmic microwave background or the distribution of galaxies. Similarly, if dark matter arises from extra dimensions, experiments searching for gravitational waves or particle collisions might uncover evidence of its existence. So, what does this mean for our understanding of the universe? Quantum gravity theories open up exciting new possibilities for explaining dark matter, suggesting that it might be deeply connected to the fabric of spacetime and the quantum world. While we're still far from a definitive answer, these ideas challenge us to think beyond traditional particle-based models and explore the profound interplay between gravity, quantum mechanics, and the cosmos. As we continue to unravel the mysteries of dark matter, quantum gravity might just be the missing piece of the puzzle. And with that, let's move on to another captivating topic: how quantum gravity theories attempt to explain the conditions of the early universe. Stay tuned as we journey back to the very beginning of everything. Now, let's take a step back in time, way back to the very beginning of the universe. Quantum gravity theories don't just help us understand the cosmos as it is today. They also offer fascinating insights into how everything began. To explore the early universe, we need to venture into a realm where time and space as we know them break down and quantum effects reign supreme. This is where the story of the Planck epoch comes into play. The Planck epoch is the earliest moment in the universe's history, a fraction of a second after the Big Bang, when the universe was unimaginably small and dense. At this scale, the effects of quantum gravity dominate, and our classical understanding of physics simply doesn't apply. Here, spacetime itself is thought to be a seething, chaotic foam, with quantum fluctuations creating tiny ripples that could have set the stage for everything that followed. Some theories suggest that during this epoch, spacetime wasn't smooth, but instead a dynamic, ever-changing network of quantum connections. This quantum foam might have been the seed from which the universe as we know it grew. As the universe expanded and cooled, it entered a phase known as cosmic inflation. This rapid expansion, driven by a mysterious form of energy, stretched the quantum fluctuations from the Planck epoch across vast distances. These tiny ripples eventually became the seeds for galaxies, stars, and all the structures we see in the cosmos today. Quantum gravity theories propose that inflation wasn't just a random event but a natural consequence of the universe's quantum origins. In some models, inflation is seen as a quantum process, where the energy driving it arises from the same quantum fields that govern spacetime itself. But what about the origin of spacetime? Quantum gravity theories challenge the idea that spacetime has always existed. Instead, they suggest that spacetime itself emerged from a more fundamental quantum reality. In loop quantum gravity, for example, spacetime is made up of discrete loops that weave together to form the fabric of the universe. At the very beginning, these loops might have been tightly packed, creating a quantum state where time and space as we know them didn't yet exist. As the universe expanded, these loops stretched and connected, giving rise to the spacetime we experience today. Other theories, like string theory, propose that spacetime emerged from the interactions of fundamental strings or branes vibrating in higher dimensions. In this view, the early universe was a chaotic dance of strings and branes, with spacetime crystallizing out of their interactions. This idea not only explains the origin of spacetime, but also provides a framework for understanding how the laws of physics themselves came into being. What's truly remarkable is that quantum gravity theories don't just describe the early universe, they also offer testable predictions. For instance, the quantum fluctuations from the Planck epoch should leave imprints in the cosmic microwave background, the faint afterglow of the Big Bang. By studying these imprints, scientists hope to uncover clues about the quantum nature of the early universe. Similarly, experiments probing the behavior of spacetime at the smallest scales could reveal whether it's truly discrete or continuous. So, what does all this mean for our understanding of the cosmos? Quantum gravity theories take us to the very edge of what we know, offering a glimpse into the universe's earliest moments. They suggest that the Big Bang wasn't just the beginning of matter and energy, but also the birth of spacetime itself. As we continue to explore these ideas, we're not just uncovering the history of the universe, we're rewriting the story of how everything came to be. And with that, let's turn our attention to another mind-bending topic, the role of wormholes in quantum gravity theories. Stay tuned as we explore these cosmic shortcuts and their connection to the quantum world. Now, let's shift our focus to one of the most puzzling and controversial ideas in modern physics, the black hole firewall paradox. This concept doesn't just challenge our understanding of black holes, it shakes the very foundations of quantum gravity. At the heart of this paradox lies a question that seems almost impossible to answer. What happens to information that falls into a black hole? According to classical physics, if you were to cross the event horizon of a black hole, you wouldn't notice anything unusual, at least not right away. The event horizon is the point of no return, where the gravitational pull becomes so strong that not even light can escape. But quantum mechanics tells a different story. In the 1970s, Stephen Hawking discovered that black holes aren't completely black. They emit radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. This raises a big problem. If a black hole evaporates, what happens to all the information about the matter that fell into it? Quantum mechanics says information can't be destroyed, but black holes seem to defy this rule. This is where the firewall paradox comes in. In 2012, physicists Ahmed Almary, Donald Maroff, Joseph Polchinski, and James Sully proposed a radical solution. They suggested that instead of a smooth event horizon, there might be a blazing wall of energy, a firewall, that would incinerate anything crossing it. This idea was shocking because it contradicted Einstein's theory of general relativity, which predicts that crossing the event horizon should be uneventful. The firewall would mean that the event horizon isn't just a boundary in space, it's a place of extreme violence, where the laws of physics as we know them break down. But why would such a firewall exist? The answer lies in the conflict between quantum mechanics and general relativity. If information isn't lost when it falls into a black hole, it must somehow be encoded in the Hawking radiation. But for this to happen, the radiation must be entangled with the black hole's interior. However, quantum mechanics also says that entanglement can't be shared in this way without violating something called the monogamy of entanglement. To resolve this, the firewall idea suggests that the entanglement is broken at the event horizon, releasing a burst of energy in the process. This proposal has sparked intense debate. Some physicists argue that firewalls are a necessary consequence of preserving information, while others believe they're a sign that our understanding of quantum gravity is incomplete. For example, in string theory, there are alternative ideas like the fuzzball proposal, which suggests that black holes aren't smooth objects with event horizons, but instead fuzzy, stringy structures that don't require firewalls. Similarly, loop quantum gravity offers another perspective, proposing that spacetime itself might be discrete, avoiding the need for a firewall altogether. The implications of the firewall paradox are profound. If firewalls exist, they would fundamentally change our understanding of black holes and spacetime. They would also challenge the principle of equivalence, a cornerstone of general relativity, which says that free-falling observers shouldn't notice anything unusual at the event horizon. On the other hand, if firewalls don't exist, we need a new way to reconcile quantum mechanics with gravity, one that doesn't lead to such extreme conclusions. So, where does this leave us? The firewall paradox is a reminder of how much we still have to learn about the universe. It's a puzzle that pushes the boundaries of our knowledge, forcing us to rethink some of our most cherished ideas about space, time, and reality. As we continue to explore these questions, we're not just solving a scientific mystery, we're uncovering the deeper truths that govern the cosmos. And with that, let's turn our attention to another fascinating topic: the role of wormholes in quantum gravity theories. Stay tuned as we dive into these cosmic shortcuts and their connection to the quantum world. Now, let's venture into the intriguing world of wormholes and their role in quantum gravity theories. Imagine a tunnel through spacetime connecting two distant points in the universe, a shortcut that could, in theory, allow travel across vast cosmic distances in an instant. This is the essence of a wormhole, a concept that has fascinated scientists and science fiction enthusiasts alike. But beyond their appeal as cosmic shortcuts, wormholes might hold the key to understanding some of the deepest mysteries of quantum gravity. Wormholes, also known as Einstein-Rosen bridges, were first proposed as solutions to Einstein's equations of general relativity. These hypothetical structures are like bridges that link two separate regions of spacetime, potentially allowing matter or information to travel between them. However, there's a catch. Classical physics suggests that wormholes would be incredibly unstable. They would require exotic matter with negative energy to stay open, something we've never observed in nature. This has led many to dismiss wormholes as mere mathematical curiosities until quantum gravity entered the picture. In the realm of quantum gravity, wormholes take on a new significance. One of the most exciting ideas is that wormholes might be deeply connected to quantum entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a groundbreaking idea. What if entangled particles are actually connected by tiny wormholes? This concept, known as the AR equals EPR conjecture, suggests that the mysterious link between entangled particles where measuring one instantly affects the other, no matter the distance, could be explained by a microscopic wormhole threading through spacetime. This idea bridges two seemingly unrelated concepts: Einstein-Rosen bridges and the Einstein-Podolsky-Rosen paradox which describes quantum entanglement. If true, it would mean that spacetime itself is woven together by these quantum connections, with wormholes acting as the threads. This could revolutionize our understanding of both quantum mechanics and gravity, showing that they are not separate forces but deeply intertwined aspects of the same underlying reality. But what does this mean for the possibility of traversable wormholes? While the wormholes predicted by quantum gravity are far too small for any physical object to pass through, they could still play a crucial role in the fabric of spacetime. Some theories suggest that these microscopic wormholes might help resolve paradoxes in quantum gravity, such as the black hole information paradox. By providing a hidden pathway for information to escape, wormholes could ensure that nothing is truly lost in a black hole, preserving the principles of quantum mechanics. Of course, the idea of wormholes as spacetime shortcuts isn't just about solving theoretical puzzles. It also captures our imagination. Could we one day use wormholes to travel across the universe? While this remains firmly in the realm of speculation, The study of wormholes in quantum gravity keeps the dream alive. It challenges us to think beyond the limits of classical physics and explore the strange, interconnected nature of the quantum world. As we continue to unravel the mysteries of quantum gravity, wormholes remind us that the universe is far stranger and more interconnected than we ever imagined. They offer a glimpse into a reality where spacetime is not a fixed stage but a dynamic, ever-changing web of connections. And with that, let's turn our attention to another fascinating intersection of quantum gravity and cosmic mysteries, the black hole information paradox and the latest theories attempting to resolve it. Stay tuned as we dive deeper into this cosmic puzzle, now shifting our focus to one of the most perplexing puzzles in modern physics. Let's revisit the black hole information paradox and explore how quantum gravity theories are working to solve it. The black hole information paradox strikes at the heart of our understanding of the universe, challenging the very principles of quantum mechanics and general relativity. At its core, the paradox asks a simple yet profound question: what happens to information that falls into a black hole? According to quantum mechanics, information cannot be destroyed, it must be preserved. But black holes, as described by general relativity, seem to erase information entirely, creating a fundamental conflict between these two pillars of physics. The paradox was first brought to light by Stephen Hawking in the 1970s when he discovered that black holes emit radiation, now known as Hawking radiation. This radiation causes black holes to slowly lose mass and eventually evaporate. However, Hawking's calculations suggested that the radiation emitted would be random, carrying no information about the matter that originally fell into the black hole. This implied that once the black hole evaporated, all the information about the infalling matter would be lost forever, violating the quantum mechanical principle of information conservation. This contradiction has puzzled physicists for decades, but quantum gravity theories are offering new ways to tackle the problem. One of the most promising ideas comes from the holographic principle, which suggests that all the information about the matter swallowed by a black hole is encoded on its event horizon, the boundary beyond which nothing can escape. This principle implies that the information isn't lost but is instead stored in a two-dimensional form on the surface of the black hole, much like a hologram. When the black hole evaporates, this information could be released back into the universe through Hawking radiation, preserving the integrity of quantum mechanics. Another intriguing approach involves wormholes, which we discussed earlier. The ER=EPR conjecture proposes that entangled particles are connected by microscopic wormholes, and this idea might extend to black holes as well. Some theories suggest that information falling into a black hole could be transferred through these wormholes to another region of spacetime, effectively escaping the black hole without violating any physical laws. This would mean that the information isn't truly lost but is instead hidden in a way that we're only beginning to understand. Recent developments in string theory and loop quantum gravity have also shed new light on the paradox. For instance, string theory's AD/S/CFT correspondence provides a mathematical framework where the information paradox can be studied in a controlled setting. This duality suggests that a black hole in a higher dimensional space is equivalent to a quantum system on its boundary, offering a way to reconcile the loss of information with quantum principles. Similarly, loop quantum gravity proposes that spacetime itself is quantized, meaning that the fabric of the universe has a discrete structure at the smallest scales. This could prevent information from being lost by providing a natural cutoff that preserves it. The implications of resolving the information paradox are enormous. It would not only validate the principles of quantum mechanics, but also provide a deeper understanding of the nature of spacetime and the universe itself. It could also pave the way for a unified theory of quantum gravity, bringing us closer to answering some of the biggest questions in physics. As we continue to explore these ideas, the black hole information paradox remains a powerful reminder of how much we still have to learn about the cosmos. It challenges us to think beyond the limits of our current theories and to imagine a universe where the rules of quantum mechanics and gravity are not at odds but are part of a single, unified framework. And with that, let's turn our attention to another fascinating aspect of quantum gravity: the nature of space itself and how it might be redefined by these groundbreaking theories. Stay tuned as we dive into the next chapter of this cosmic journey. Now, let's take a closer look at how quantum gravity theories are reshaping our understanding of space itself. For centuries, space has been thought of as a smooth, continuous fabric, as described by Einstein's theory of general relativity. But quantum gravity challenges this notion, suggesting that space might not be as seamless as it appears. Instead, it could be made up of tiny, discrete units at the smallest scales, fundamentally altering how we perceive the universe. One of the key ideas in this realm is that space-time might be quantized, meaning it's composed of indivisible building blocks. Think of it like a digital image. From a distance, it looks smooth and continuous, but when you zoom in, you see it's made up of individual pixels. Similarly, quantum gravity proposes that space-time has a granular structure at the Planck scale, the smallest possible size in the universe. This idea is central to theories like loop quantum gravity, which suggests that space is woven together by tiny loops or networks, creating a fabric that's fundamentally discrete rather than continuous. This shift from continuous to discrete space-time has profound implications. For one, it could resolve some of the infinities that plague classical physics, such as the singularities found at the center of black holes or the Big Bang. In a quantized spacetime, these infinities might be smoothed out, offering a more complete picture of the universe's most extreme environments. It also raises fascinating questions about the nature of reality itself. If space is made up of discrete units, does that mean the universe operates more like a computer, processing information at the smallest scales? Some physicists even speculate that this could hint at a deeper, underlying structure to reality, one that we're only beginning to uncover. On the other hand, some theories, like string theory, still treat spacetime as continuous but introduce extra dimensions to explain quantum gravitational effects. This creates a tension between the discrete and continuous views of space, each offering unique insights into the nature of the universe. The debate between these perspectives is far from settled, but it's driving some of the most exciting research in modern physics. The implications of redefining space extend beyond theoretical physics. If spacetime is quantized, it could influence everything from the behavior of particles to the evolution of the cosmos. It might even change how we think about time, causality, and the very fabric of existence. As we continue to explore these ideas, one thing is clear: our understanding of space is far from complete, and quantum gravity is leading the charge in uncovering its true nature. With this new perspective on space, we're ready to explore another intriguing aspect of quantum gravity: how it challenges our understanding of reality itself. Stay tuned as we dive into the next chapter of this cosmic journey, where we'll examine the profound ways quantum gravity theories are reshaping our view of the universe. Now, let's shift our focus to one of the most mind-bending aspects of quantum gravity: how it challenges our very understanding of reality. Quantum gravity doesn't just reshape our view of space and time, it forces us to rethink what reality itself might be. At the heart of this exploration are concepts like superposition, entanglement, and the observer effect, ideas that blur the line between the familiar world we experience and the strange, counterintuitive realm of quantum physics. Take superposition, for example. In the quantum world, particles can exist in multiple states at once until they're observed or measured. This means an electron isn't just here or there, it's both simultaneously. Quantum gravity takes this idea even further, suggesting that spacetime itself might exist in a superposition of states. imagine a universe where the fabric of reality isn't fixed but fluctuates between countless possibilities. It's a radical departure from the classical view where reality is solid and predictable. Then there's entanglement, a phenomenon Einstein famously called spooky action at a distance. When particles become entangled, their properties are linked no matter how far apart they are. Change one and the other instantly responds, as if space and distance don't matter. Quantum gravity theories propose that entanglement might be deeply connected to the structure of spacetime itself. Some researchers even suggest that spacetime could emerge from a vast network of entangled quantum states, weaving together the universe in ways we're only beginning to understand. And let's not forget the observer effect, which highlights the role of observation in shaping reality. In quantum mechanics, the act of measuring a system can fundamentally alter its state. Quantum gravity extends this idea, raising questions about whether the universe itself might be shaped by observation. Could the presence of observers, whether conscious beings or physical interactions, play a role in determining the structure of spacetime? It's a provocative thought that challenges our assumptions about an objective, independent reality. These ideas don't just exist in the realm of abstract theory. They have real implications for how we understand the universe. If reality is fundamentally quantum in nature, then our classical notions of cause and effect, space and time, and even existence itself might need to be reimagined. Quantum gravity invites us to consider a universe that's far more dynamic, interconnected, and mysterious than we ever imagined. As we continue to explore these concepts, one thing becomes clear. Quantum gravity isn't just about understanding the universe, it's about redefining what it means to exist within it. And with that, we're ready to dive into the next chapter of this journey, where we'll examine how quantum gravity intersects with experimental tests and the challenges of proving these groundbreaking ideas. Stay tuned, the adventure is just getting started. Now, let's turn our attention to a crucial question. How do we test these mind-bending theories of quantum gravity? After all, ideas like superposition, entanglement, and spacetime fluctuations are fascinating, but without experimental evidence, they remain in the realm of speculation. This brings us to Theory 29, Quantum Gravity and Experimental Tests. Here, we'll explore the challenges scientists face in testing quantum gravity and the innovative efforts underway to detect its elusive effects. One of the biggest hurdles in testing quantum gravity is the scale at which these effects occur. Quantum gravity operates at the Planck scale, which is unimaginably small, about 1/trillionth of a trillionth of the size of an atom. At this scale, the effects of quantum gravity are so tiny that they're incredibly difficult to measure with current technology. To put it simply, we're trying to detect something that's happening in a realm far beyond what our most advanced instruments can currently observe. But scientists aren't giving up. One promising approach involves studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. Tiny fluctuations in this radiation could hold clues about quantum gravitational effects in the early universe. Another avenue is gravitational wave astronomy. When massive objects like black holes collide, they send ripples through spacetime. By analyzing these ripples with detectors like LIGO and Virgo, researchers hope to find subtle signatures of quantum gravity. Particle accelerators also play a role. While they can't directly probe the Planck scale, they can test predictions from theories like string theory or loop quantum gravity. For example, if extra dimensions exist, as some theories suggest, particle collisions might produce unusual patterns that hint at their presence. Similarly, experiments with ultra-cold atoms and quantum systems are being used to simulate quantum gravitational effects in controlled environments, offering indirect insights into how spacetime might behave at the smallest scales. Despite these efforts, the challenges remain immense. Quantum gravity effects are incredibly weak compared to other forces, and isolating them from background noise is like trying to hear a whisper in a thunderstorm. Plus, many theories of quantum gravity make predictions that are currently beyond our ability to test. This means that, for now, much of the work in this field is theoretical, relying on mathematical consistency and logical coherence rather than direct experimental evidence. Yet, the pursuit of experimental tests for quantum gravity is far from hopeless. New technologies and collaborations are pushing the boundaries of what's possible. For instance, space-based observatories and next-generation gravitational wave detectors could provide the precision needed to detect quantum gravitational signals. And as our understanding of quantum mechanics and general relativity deepens, we may discover new ways to bridge the gap between theory and experiment. So, while the road to testing quantum gravity is long and fraught with challenges, the journey itself is driving some of the most exciting advancements in physics. Every experiment, every observation, and every theoretical breakthrough brings us one step closer to unraveling the mysteries of the universe's deepest structure. And with that, we're ready to move into our final theory, where we'll explore the future of quantum gravity research and the tantalizing possibility of a unified theory of everything. Stay with us, this is where the story gets even more fascinating. As we step into the final chapter of our exploration, let's take a moment to look ahead. The future of quantum gravity research is brimming with possibilities, and the questions we're asking today could reshape our understanding of the universe tomorrow. Theory 30, the future of quantum gravity, invites us to imagine what lies beyond the horizon of current knowledge, a frontier where science and speculation meet in the pursuit of a unified theory of everything. One of the most pressing open questions in quantum gravity is whether spacetime is fundamentally continuous or discrete. While theories like loop quantum gravity suggest spacetime is made up of tiny, indivisible units, others, like string theory, propose a smooth, continuous fabric. Resolving this debate could unlock profound insights into the nature of reality itself. But how do we get there? The answer lies in the development of new mathematical tools and experimental techniques that can bridge the gap between the quantum world and the cosmic scale. Emerging theories are also pushing the boundaries of what we thought was possible. For instance, some researchers are exploring the idea that quantum gravity might not be a single theory but a family of interconnected frameworks, each valid in different contexts. This theory of theories approach could provide a more flexible way to describe the universe, accommodating the strange and often contradictory behaviors we observe at quantum and cosmic scales. Meanwhile, others are investigating whether quantum gravity could be linked to other fundamental mysteries, like the nature of dark matter and dark energy, offering a unified explanation for the universe's most elusive phenomena. The dream of a unified theory of everything, a single framework that explains all the forces and particles in the universe, remains the ultimate goal. While we're still far from achieving this, the progress made in quantum gravity research is bringing us closer than ever. For example, the AD/CFT correspondence, a duality between gravity in higher dimensions and quantum field theory, has provided a powerful tool for exploring how gravity and quantum mechanics might fit together. Similarly, advances in quantum computing and simulations are opening new avenues for testing quantum gravity theories in ways that were previously unimaginable. But the journey doesn't end with theory. The future of quantum gravity research will also depend on groundbreaking experiments. Next-generation observatories like the Einstein telescope and space-based gravitational wave detectors could provide the precision needed to detect subtle quantum gravitational effects. Meanwhile, particle accelerators and quantum simulators might uncover unexpected phenomena that challenge our current understanding and point the way toward new theories. As we stand on the brink of these discoveries, it's worth reflecting on how far we've come. From the early days of general relativity and quantum mechanics to the cutting-edge ideas we've explored in this video, the quest to understand quantum gravity has transformed our view of the universe. And while many questions remain unanswered, the pursuit of knowledge itself is a testament to human curiosity and ingenuity. So, what does the future hold? Perhaps one day we'll uncover a theory that unites all the forces of nature, revealing the universe's deepest secrets. Or maybe we'll discover that reality is even stranger and more beautiful than we ever imagined. Whatever the outcome, the journey to understand quantum gravity is far from over, and the next chapter promises to be the most exciting yet. Thank you for joining us on this incredible exploration of the universe's quantum mysteries. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell to stay updated on our latest adventures into the cosmos. Until next time, keep wondering, keep exploring, and keep reaching for the stars. As we bring this journey through the 30 theories of quantum gravity to a close, it's clear that each one offers a unique lens through which we can view the universe's deepest mysteries. From loop quantum gravity's discrete spacetime to string theory's vibrating strings, and from the holographic principle's boundary encoded reality to emergent gravity's entropic origins, these theories collectively push the boundaries of our understanding. They remind us that the quest to unify quantum mechanics and gravity is not just about solving equations, it's about reimagining the very fabric of reality. What ties these theories together is their shared ambition to answer some of the most profound questions in science. How did the universe begin? What happens inside a black hole? Is spacetime continuous or made of tiny building blocks? While each theory approaches these questions differently, they all contribute to a richer, more nuanced picture of the cosmos. Together, they highlight the incredible creativity and persistence of scientists striving to uncover the universe's secrets, but the story doesn't end here. The exploration of quantum gravity is a living, evolving field with new ideas and discoveries emerging all the time. Whether it's through groundbreaking experiments, innovative mathematical frameworks, or bold theoretical leaps, the future of quantum gravity promises to be as exciting as the theories we've explored today. And while we may not yet have a unified theory of everything, the progress we've made so far is a testament to the power of human curiosity and collaboration. So, what's next for you? If this journey through the mysteries of quantum gravity has sparked your curiosity, why not dive deeper? Share your thoughts in the comments below. What theory resonated with you the most? Or if you're eager to learn more, check out the links in the description for further reading and resources. Don't forget to like, subscribe, and hit the notification bell so you never miss an update as we continue to explore the wonders of the universe. Until next time, keep asking questions, keep exploring, and keep marveling at the incredible complexity and beauty of the cosmos. The universe is waiting for you to uncover its secrets.